Rosemount has invested several $1,000,000 into this flow lab for the development of our products for research, development, and training. We utilize the capabilities of this flow lab to prove our products and technology, positioning Rosemount as the best in the market. Today we will be demonstrating the revolutionary conditioning orifice plate under several conditions to show the superior performance of this technology. Our first demonstration, we have placed a butterfly valve upstream of the conditioning orifice plate. Normally, a butterfly this close to a meter will disturb the performance of the meter, but the conditioning orifice plate acts very well under these conditions. We'll leave the valve fully open and then close it slightly. To demonstrate the flow through the acrylic pipe, we'll add some air bubbles upstream that will show the upstream and downstream flow on either side of the plate. As you can see, we have started the flow through the pipe. You'll see just after the butterfly valve, there's a highly turbulent area, and as we close the valve slightly, it adds even more turbulence and distortion to the flow. If we look on the downstream side of the conditioning orifice plate, you'll see a highly mixed, highly turbulent area which stabilizes and conditions the flow signal so that the upstream effects are not affecting the performance of the meter. Now that you've seen the visual demonstration of flow through a conditioning orifice plate, we want to show you an actual flow meter measuring differential pressure downstream of the butterfly valve. The idea of this demonstration is to show you that as you have a fully open or partially closed butterfly valve, the performance measurement of the meter does not change. As you can see on the monitor, the flow rate remains steady and the DP signal is steady. As we close the valve slightly upstream of the conditioning orifice plate, the flow rate remains at the same level, and also the DP level stays at the same measurement, which means the performance of the conditioning orifice plate is not affected by the valve upstream. To demonstrate the performance of a standard orifice plate downstream of a butterfly valve, we have switched out the conditioning orifice plate and replaced it with a standard orifice plate. As you can see on the monitor, we are still demonstrating flow rate and differential pressure on the screen. As we close the valve slightly upstream of the standard orifice plate, again the flow rate remains constant, but the differential pressure measurement changes, affected by the change of the valve upstream. The second part of this demonstration, we'll be moving from the 4-inch acrylic section and reducing down to a 3-inch section of pipe with multiple elbows out of plane. What we want to show with this demonstration is that inadequate distance downstream of a disturbance can affect the flow very dramatically. As you can see in this clear section, the flow is swirling down the pipe as it exits the double elbows out of plane. Obviously, this is not an ideal condition to put in a flow meter in such a disturbed flow condition. So let's put in a conditioning orifice plate in the recommended position 2 diameters downstream of the double elbows out of plane. As you can see, the flow is very turbulent and mixed again downstream of the conditioning orifice plate, and the effect of the double elbows out of plane is virtually gone, meaning that the measurement is accurate even though it's so close and in such disturbed flow conditions. In summary, we have shown you the unmatched superiority of the conditioning orifice plate and how it performs under different flow conditions, specifically under flow disturbances with short straight run piping. Hopefully you now have a better understanding of the conditioning orifice plate and how you will be able to utilize this technology in your application needs.